In this video, we're going to look at isolated points for a set of real numbers. We will start with the following definition. You should stop the video and copy this definition down in your notes very, very carefully. So hopefully you've done that. What I want to do is I want to start by what does it really mean when we say that little m is an isolated point for the set capital M. So when we say little m is an isolated point for capital M, which is some subset of the real numbers, what this means is that if we draw a number line and we put M on this number line, then we can find some open interval, and it does not have to be a balanced open interval. So here's an open interval that contains little m, and little m is in set capital M, and little m is the only element of capital M inside O. In other words, if I look at the punctured open interval, if I look at O, take away the set containing little m, which is all of this red stuff, there are no elements of set M inside this red area. And in other words, the set O take away the set containing little m intersected with M is going to have to be empty. Another way of saying this is that O intersected with M is the singleton set containing just little m. Now, there's nothing special about open intervals, and that brings us to the next problem which I want to look at, which is problem 53. Problem 53 asks us to explain why an isolated point has the property that we can find a delta ball centered at that isolated point, such that the intersection with the set M is just the singleton set containing little m. You should definitely stop the video and copy this example down as well. And you should try and work this example before restarting the video, and then compare your solution to the work that I will do. So hopefully you've done that. So how would I go about solving this problem? Well, this is what I would basically think about doing. We're going to start off by letting little m be an isolated point for set capital M. So what does that say? That says here's the number line, and here's little m on that number line. And because of this, I know that there exists a capital O that contains little m, such that capital O intersected with capital M is just the singleton set containing little m. In other words, if I look at O on this number line, this is the only element of M that is inside the open interval O. Now, because O is an open interval, so because O is an open interval, and let me make my handwriting just a little bit easier to read. And because little m belongs to O, we know that there exists a delta bigger than 0 such that the delta ball centered at little m of radius delta is a subset of O. So I'm going to actually draw that delta ball. So let's draw that delta ball. So we'll go out delta in this direction, and we go back delta in this direction. And so this particular interval here is the delta ball centered at M of radius delta. And what I want to notice is the following. I want to note that the delta ball is a subset of O, and so the delta ball intersected with capital M has to be a subset of O intersected with capital M, but O intersected with capital M is just the singleton set containing just little m. And I also know, so I know that little m does belong to this delta ball, and little m does belong to capital M. So what does that tell me? That tells me that little m does belong to the intersection of the delta ball and m. And that says the singleton set is a subset of this intersection. And we've already seen that the intersection has to be a subset of the singleton set containing little m, and that forces the intersection of the delta ball with m to be nothing more than the singleton set containing little m. I want to end with one final little observation that this particular problem that we were looking at does go both ways. So let's just write that as an observation. So an observation. If I can find, so if there is a delta bigger than 0, such that the delta ball centered at M of radius delta intersected with the set M is just the singleton set containing M, then that will imply that M is an isolated point for the set M. And the reason why is actually pretty straightforward and simple. It's the definition of isolated point. This particular delta ball is an open interval that contains little m, and little m is an element of capital M. So if that delta ball intersected with capital M is just the singleton point little m, then we've satisfied the definition of isolated point. So M satisfies the definition of isolated point because we have found an open interval where the intersection of the set capital M and the open interval is just the singleton point. And so we're actually done. So what this means is that to show a particular point, and let's write this on a own page. So to show little m is an isolated point for capital M, what we need to do is we need to show, first of all, that little m does indeed belong to capital M, and then we need to show that there does exist a delta bigger than 0 such that the delta ball centered at M of radius delta intersected with set M is just that singleton set, or equivalently, and let me clean up my handwriting there. So equivalently, we can show that the punctured delta ball intersected with M is the empty set. And the reason why that last is true, just to remind you, is that if I have a punctured delta ball, if I draw a delta ball here, and that should be centered at M, all I do is delete this point from the open interval, and I am now looking at the delta ball that is punctured, and so little m is never an element of the punctured delta ball. And so that's why this second statement is equivalent to the first statement.